Good afternoon, everyone. Welcome to the session. Today, I'll talk about scaling large language model post-training at Character.AI. I'm Haoran, and I'm currently leading the post-training and data research team in Character.AI. In case you don't know, Character.AI is the leading application for AI entertainment. We are serving tens of millions of users per day with large language models. To continuously improve the model that power our AI characters, we have built a robust and scalable post-training stack entirely on open source technologies in the Ray ecosystem. The agenda for this talk is I'll first talk about our fine-tuning stack, internally named Rayman, which has allowed us to accelerate our development velocity and improve large MOE model training efficiency. And specifically, I'll cover distributed training with RayTrain and data processing with Ray Data and our in-house distributed training engine pipeline SFT and how we do SFT or DPO. And in the next session, I'll talk about how we do RL from real user interactions. I'll cover our RL framework, reward modeling, and our reward function. So Rayman is our internal post-training framework built on Ray Data RayTrain for orchestrating the distributed workloads. It supports efficient training of large-scale 600 billion plus parameter MOE models. It uses hydroconfig for easily modifying training configurations and launching sweeps. It integrates with our internal data storage for efficient data loading and processing. And we also have some custom optimizations for large-scale MOE model training. We mainly use Rayman for SFT and DPO kind of fine-tuning. So Rayman uses RayTrain as the orchestrator layer for multi-node distributed training. On the right side is a code snippet of how we use Torch Trainer. We can see that the trainer supports dynamic scaling with scaling config and automated model checkpointing with configurable retention policies and best model selection. In Rayman, we support DeepSpeed, FSDP, and our in-house pipeline SFT as distributed training engine. And data processing is using Ray Data. The benefit of using Ray Data is every dataset operation runs in parallel across all the Ray workers. Specifically, Ray Data integrates with the Ray's cluster scheduler, and it can automatically allocate resource across nodes. And Ray Data reads from GCS Parquet files with high concurrency, which is our main data storage. In addition, Ray Data supports streaming rates and lazy processing. So you don't need to pre-tokenize your entire dataset before training actually begins, which significantly slows down startup time for larger datasets. And it does zero copy batching and data repartitioning for efficient memory usage. Next, I'll talk about the in-house MOE training framework we built called Pipeline SFT, which is also open sourced. And you can find the open source repo in our Character.AI blog. So the motivation of building this new training framework is, at that time, open source solutions we explored didn't work when scaling up to fine-tuning DeepSeek. And we also found some room for improvement. So our pipeline SFT supports multi-level parallelism, including pipeline parallelism, expert parallelism, and the tensor parallelism. Its sharding strategy is pipeline parallelism across nodes and expert and tensor parallelism across 8 ranks within each node. Since expert parallelism incur all-to-all communication. So we want to keep the expert groups within a node. And our pipeline SFT supports both BF16 and FP8 training. It also does some custom optimizations for training stability, including gradient synchronization and mixed pre-series optimizers, which I'll detail in the next slides. It also has a seamless Hugging Face integration that allows training from Hugging Face model weight directories and export directly back into Hugging Face checkpoint format. One optimization that was done is we implemented a custom mixed pre-series LLM optimizer that maintains the master weights in FP32 while the forward and backward computations are kept in BF16. We found that this introduces minimal memory overhead with training speed nearly unchanged, but it enables stable convergence at low learning rates. And a DeepSeek technical report also demonstrated full pre-series master weight is required for the loss convergence, and the lower pre-series optimizer state is sufficient. However, the native PyTorch item optimizer forces the optimizer states to be in the same pre-series as the parameter D type, which is less memory efficient. While our custom mixed pre-series LLM supports lower pre-series optimizer states with full pre-series master weights. You can see from the right figure below where the green curve is with our mixed pre-series LLM, and the orange curve is with the BF16 LLM. You can see that the standard LLM with BF16 fails to converge, while our mixed pre-series LLM convergence smoothly with the minimal training slowdown and memory increase. Another thing we did is adding gradient sync functions in both MLA and MOE layers, which help to prevent training divergence across distributed ranks. So why we need to do that? So MLA uses shared learnable position embeddings across the attention heads for K projections, which means that when tensor parallel is enabled for attention, position embedding receive different gradients in the backward pass for different sets of attention heads. So if we don't add the backward hook to sync gradients for positional embedding of K, then gradients will start to diverge across the replicated parameters within the TP group. And for MOE, most MOE forward uses the indices masking to efficiently run the experts on selected tokens and then accumulate results coupled with the corresponding expert in an output tensor. But due to the numerical accuracy issue of PyTorch matrix operations, there will be differences in gradients for replicated parameters within the expert parallel group. So we also need to add the explicit gradient hooks in the backward for MOE layer. As you can see from the right side graph, the green is with the gradient sync and orange is without. So without using gradient sync, training is very unstable with the gradient norm exploding, if you see the false graph. And then the loss curves is also a bit higher. So one major issue with BF16 training is that serving becomes very expensive. So BF16 version of DeepSeek v3 requires multiple nodes for one instance, where we know the internode communication is much slower compared to the intranode, while the FP8 version could fit in a single node. So when we enable use FP quantization to export our fine-tuned checkpoints in FP8 with DeepSeek's official blockwise quantization algorithm, we notice that without proper quantization-aware training, naive export time quantization diminishes the effect of fine-tuning. So we ended up implementing the FP8 mixed precision training described in the DeepSeek technical report. But to support FP8 training, we use DeepGem, which does efficient FP8 matrix multiplication and FP32 accumulations to mitigate the loss in precision. But DeepGem only provides efficient kernels for matrix multiplication operation, while other aspects like quantizing the activations and the weights are not fused, which makes the entire FP8 linear layer very inefficient. So naively, our custom FP8 linear class is roughly 10 times slower than the native PyTorch BF16 linear class. We then implemented a custom fused version of these quantization operations and managed to get a 2 to 3 times speed up. Regarding where we use Rayman, so we mainly use Rayman for SFT and DPO kind of fine-tuning. So one example use case is we do SFT on user chats. So why SFT on user chats could help? So an important feature we have is swipe. So users can swipe to generate a different response, and then they can choose one response to continue with. So we have a highly engaged user base where our users generate a lot of swipes data for us. So in fact, we get around 200 million bot turns with swipes per day. And with some quality filtering and use the chosen response from user swipes, it's like a user-guided rejection sampling data. As we know, rejection sampling helped improve model performance in many papers. Also, choosing after swipe is also an important reward model for us. Another major use case is to use user chat with expensive high-quality models to distill into more cost-efficient models. So when we use user chat data to do distillation, so we found filtering the low-quality data and data diversity are very important. Besides SFT, we also leverage the user data flywheel for DPO training, including the user swipes data I just mentioned, and we also have user side-by-side preference data, and some synthetic data, preference data targeting issues of the model from user feedback. So user preference data are very noisy, so it's important to do a bunch of filtering to pick the less noisy data. For example, making sure it's from a safe user, and limiting individual user influence, and avoiding the conversation that user swipes too often, and making sure users spend enough time reading the message before they make a choice, and combined with other filters. So that's about our fine-tuning stack. So next, I'll highlight our IO work. So a core challenge in aligning models for open-ended creative dialogue is that there are no verifiable rewards. At Character, we are serving 20 million users with tons of user interactions. So in this section, I'll talk about how we utilize our rich user interactions data to do reinforcement learning to continuously enhance the model quality and drive engagement. So without any spending on data labeling, and can directly result in online engagement gains. Our IL training framework is based on internal fork of Verl with the integration of internal data processing. So Verl is also using the Ray ecosystem. On top of Verl, we train our own user signal reward models and have custom reward function for IL training. So a core part of our IL work is in reward modeling. So a judgment of which response is better is quite subjective in our use case. So before going to the reward modeling, let's talk about how we evaluate our model first. So how do we measure something as subjective as a fun and engaging conversation? So we designed several metrics using principles of compelling writing with the help of professional writers, consisting of a combination of creative writing techniques and objective dimensions such as novel contribution, is this response a descriptive language, is it a gesture, etc. And in addition to that, there are common quality judges of safety, whether the response stays in character, good or bad memory, and repetition, etc. And besides that, another key thing to look at is a reward model score trained with user preference. But in the end, it depends on the online A/B result. So for online test, of course, we need to first make sure safety meets the bar. But then what matters is engagement metrics like session count, time spent, and most importantly, retention, like L1D1, L1D7, and DAU. If you optimize for metrics defined by yourself, so often you will find when you deploy the model online and do real A/B, like it might not result in engagement or retention gains, which is what we care about. So for reward modeling, in addition to the common quality and user preference reward models, we also focused on building reward models using engagement signals. For example, we're trying to predict like a number of future turns, whether a user continues the conversation, time to next response, etc. And in addition, we also trained reward models to predict longer-term retention, such as whether a user comes back next day, comes back in 7 days. In terms of performance, the number of future term regression model can get around 0.56 R square, and the binary version of its continue model can get around 75% AORC. And the retention model predicting whether user returns next day gets around 84% AORC. And the one predicting whether user is active after 7 days gets around 83 AORC. So the accuracy is actually pretty high for the retention prediction. We suspect that it might learn some shortcut features, but we think it might be fine with some RL algorithms as long as it learns other signals too, since like compounding factors will be canceled out in the advantage calculation, which I'll talk about later. But overall, like this retention thing is something like we are still experimenting with, and the A/B result for that hasn't been finalized yet. And for quality judge and some of more like objective dimensions such as novel contribution can be from LLM judge. And some could use the user feedback pills data. So pills data is when user clicks thumbs up or down, like we give them a list of reasons to choose from. So for user preference, right now, like we're mainly using the choose after swipe data that I mentioned earlier. And there are other user signals too, such as user edit, thumbs up and down, and some others that we haven't prioritized based on our data analysis, since we didn't find like a strong correlation with retention. So we built some custom reward functions on top of Verl. A simple baseline is a weighted sum using a heuristic weight. And we can also learn the ways to maximize a true KPI like 7-day retention using our historical logs. And a more sophisticated reward function is a multi-objective with a constraint. So for certain aspects such as safety and other issues, so we want the model to strictly adhere to those constraints. And we can implement as like a soft constraint using a Lagrangian with a high safety threshold tau, for example. Or we can also set like a hard mask, like if the safety score is smaller than tau, then we force the reward to be negative key, where a key is some large value. On the RL algorithm side, so PPO used to be the most popular option, which is what the original InstructGPT paper used. So PPO like updates the policy by maximizing the objective shown here. It introduces like a clipped surrogate objective for policy optimization. And the advantage is computed using the generalized advantage estimation using the reward function, which is the R here, and the value function is given by the critic model. By constraining the policy updates within a proximal region of the previous policy using clip, so PPO stabilizes training and improves the sample efficiency. But PPO is quite heavy. So in the back to basic paper from Cohere, they show that some far simpler reinforced style optimization variants could outperform PPO. Among those variants, like ALU performs best in their experiment. And with ALU, there is no need for a separate critic model. And the advantage of each sample is estimated by subtracting its reward with the average reward of all other samples from the same prompt. As shown as the advantage function. This reduces gradient variance compared to a raw reward signal. And it's computationally much cheaper than PPO. And then DeepSeek proposed like a JRPO, which also provides a separate, which also avoids a separate critic model, and use the normalized reward across the group as an advantage estimate. So the normalization here improves stability, and JRPO thus can handle large batches and diverse reward scales better. And there is a K-out term in the DeepSeek JRPO equation to like prevent the new policy from straying too far from the old one in a single update. We found like that's usually necessary for RLU2 to stabilize training. And a PPO in the Instruct GPT paper also added a KL penalty in the reward for advantage calculation. So we empirically find like a GRPO is more stable compared to RLU, and can usually train for like more steps with the same reward function. But in some cases, the variance scaling term in GRPO like will bias towards more deterministic generations, since like lowering the variance leads to like a higher reward for the winner. So we see some initial promising results from RL with engagement reward models. This is just a result of one example run. And this run is with the continual reward model. And in our experiments, like RL model with the number of future turns like achieve similar performance. We can see that as we do RL with its continuum model, the engagement score calculated by the same model on the validation data keeps increasing. And after a certain number of steps, it's like 1K steps with 1K batch size in our use case. In our case, and then it runs into like a reward hacking issue. And on the right side is a A/B result with like 1K step checkpoint. And the result is comparing the IL model to the base SFT model before doing IL. We can see that like a number of human messages is up by 9%, which is what this specific engagement reward model is optimizing for. But as a result, like time spent is also up by 9%, and session count is up by 4%, and DU is also up by more than 3%. So we still like want to scale our IL further. So we are currently experimenting with like a combination of multiple reward models, which allow us to like train for longer steps without mood collapse and bring even more improvement. So we haven't finalized the result for that yet, so it's not shown here. So for like ongoing and future work, we are still enhancing our IL framework, and we are trying to find the best recipe for roleplay and creative storytelling, and expanding our model capabilities around tool use and roleplay reasoning. So before I ramp up, I want to take a moment to recognize the incredible team behind this work, and thanks to all our contributors here. That's all for my talk, and thank you for attending the session. And any question? I can't see.
A very nice talk. One of the questions is, I noticed that you are gathering metrics from online, right? So does that mean that actually you are incorporating your IO like a loop, also getting, you update your weights based on what you get online, then you just update your weights again, then redeploy online? Do you do it like this, or purely it's offline? You just write your role model?
We don't do like it's not like a total online training, but like we continuously like accumulate like the data to train our like engagement reward model, and then we use the reward model to do like IO, and then we deploy, and then we recollect data, retrain the reward model. It's like
Another question. So one of the problem we are encountering is long horizontal, like multi-round chatting, and the reward is very delayed, right? How you resolve that issue? I think that's the
so I think some of our reward models are intended to capture like a longer term. For example, like instead of looking at a single turn, like we are predicting like a number of future turns, and we are like trying to predict like a longer term retention. Internally, like we are also experimenting like with multi-turn IL to make sure to like optimize like for multiple turns.
I'm sorry, I know there are more questions, but we need time to have the audience rotate for the next session. Could you catch her right outside the room? Can you give either your contact information or answer their questions, please?
Sure.
Thanks.
Thank you.